Hi everyone. So now let's discuss one more problem. It's a searching problem. As the name says, it's a rotated search problem. Okay. So let's see what is the problem statement. It says write a function that takes input a sorted array of distinct integers which is rotated about a pivot point. Okay. And you need to find the index of any given element. It's not a completely sorted array, but instead it has been rotated. For example, this part of the array is there and the next elements of the array, they were rotated and they went to the front of the array like this 7 9 10. Okay. So it's not a completely sorted array, but if you try to visualize this array, maybe let me give a small example. 1 2 3 4 5, let's say this was a sorted array, and if you rotate maybe about this point, let's say you rotate about 3 or 4, it will become something like this: 4 5 1 2 3. And you need to perform search. Maybe I say, okay, tell me where the element 2 is present. Okay, and you want to use an efficient searching algorithm, you don't want to do linear search, so we need to come up with a modified binary search on this particular problem. Let us try how we can solve such a problem using binary search. So I have uh, this array. Okay. Yeah, so let's say this is the array. I just updated the input because it was not correct. So now we have these elements in the array and we want to see where a particular element will lie. So if you try to visualize this, okay, so the best way to solve such a problem is to visualize how the data lies. Maybe I will draw a curve. So maybe we have 0 1 and 3. So maybe 0 1 2 and 3. So these elements lie like this. Then we have 4 5 6 7. They also lie on a monotonic curve. So the curve is now broken. So instead of having a single increasing curve, we now have two curves because it's broken about a point. So we have 4 5 6 and 7. So there are two ways. One way is you first find out a pivot element. Maybe you find out where this pivot lies, and depending upon whether your element lies in this part or in this part, you can do binary search on one of these. Okay, so that is one way, but we can also solve this problem without finding the pivot. Okay, without finding pivot. So let me say, so this is the observation, right? So if you see, this element will be smaller than or equal to this particular element that you have here. Now, how do we do binary search? That's what we need to look at. So let us first find out the midpoint. Let's say this is my start, this is my end. I find out the midpoint. Now the midpoint can either lie on this curve or it can also lie on this curve. So there are two options, maybe option 1 or option 2. Okay, so I will come to option 2 later, but it can lie on this curve as well. So maybe on line 1 the mid can lie, or on the line 2 the mid can lie. So let us assume the midpoint lies on line 1. Then what happens in that case? Let's say you're looking for an element that is, let's say, 4.5. Okay, and let's say the midpoint is pointing to this element 5, or let's say the midpoint is pointing to the element 6. Let's say this is the mid as of now. So what you can do, you also know the start, you also know the mid, and you also know the end. So how do you know whether the mid lies on line 1 or mid lies on line 2? So that is pretty easy to check. If array of start is less than equal to array of mid, then can you make any assumption? So it lies on line 1, because you can see if mid lies here, then this starting element will not be greater than mid, or will be greater than mid. Okay, if the starting element is less than equal to mid, that means this mid lies on line 1. But if you have a second case, if mid lies here, okay, let us say the mid lies here. So if array of mid is less than equal to array of end, okay, this will be the case only if mid lies on line 2. So that means the mid lies on line 2. So we'll come to this case later on, but I've told you the condition, right? So once you know this, you can divide your problem into two parts. So one part would be this part, okay, from array of start till array of mid. The other part would be from array of mid plus 1 till array of end, okay, mid plus 1 to end. Now how do you know in which part your element is going to lie? So let us talk about the first case. The mid lies on line 1. So how do you know whether to make a call on the left or to make a call on the right? So you can see the right part is broken. You cannot make a comparison directly in the right part, but you can check whether the element lies in the left part or it does not lie in the left part. So you can make a call on the left. You can reduce your problem to this line if your element, that is your key, if it lies between array of mid and if it lies between array of start. In that case you go left, otherwise you go right. Okay, so right basically means from mid plus 1 till end, and left basically means from start to, let's say, mid, and right means from mid plus 1 till the end. So you can reduce your sub problem size. So this is case 1, which also has two cases, whether to go left or whether to go right. The second case would be if mid happens to lie on line 2. So I will just draw the diagram again. Okay, so we have this line and we have this line. So if, let's say, the mid lies here, maybe this is how it looks like. This is end, this is, let's say, start. If mid lies here, then what you can do, you can check whether your data lies between array of mid and array of end. So you can check if key lies between array of end and array of start, then you can reduce your problem size to this part. You can search in this part. Okay, that means you go right. Otherwise, right basically means from mid plus 1 till the end. Otherwise you can go left. So left basically means from start to mid minus 1. Okay, from start to mid minus 1. So that means you will search in this part of the array. By just reducing the search space at every step, there will be a point when you will be able to stop your search, and either you will get the answer at the mid or you will not get the answer at the mid. Okay, so this is the whole idea. So it makes two cases. So we have two cases for the midpoint, and for each of the two cases we further have two more cases. Okay, so this type of thinking is very important. This also helps you to find out what possible corner cases could be there, because without thinking the logic, if you just start coding, you will get stuck with the cases. Okay, this problem is not difficult. The only thing is you have to handle all corner cases very properly. You may get a wrong answer, you may get a runtime error if you miss any one of these cases. So in the next video we will discuss the coding, and it's a simple modified binary search algorithm, and I will show you the code in the next video.